Yo, hello everyone. Welcome back to another video. And in today's video, I'm going to be talking about the importance and complex numbers. I've been wanting to make this video, but yeah, I was kind of busy. But now I think I have some time. So yeah, let's make this. Okay. So yeah, I think I have time. Since it's 10, I'm not gonna make this video too long, but yeah. Okay. So the first thing I want to start with is like for example, suppose like see, I'm gonna write back in the 18th to 19th centuries when imaginary numbers were discovered, they were just deemed imaginary. So what happened was that these numbers, they just thought they were useless. Like they thought that they thought like this was, they didn't want this. But but they are useful. See, imaginary numbers are not just imaginary, they are very useful fields, and so are complex numbers. Okay, so I'm just gonna keep a box here. Okay, so all we're studying here, like the quality of complex numbers, the properties, operations, the complex plane, they all have some like usefulness. Like for example, one uses the complex plane helps us in angle rotations. Yeah, like degrees. Yeah, they help us in angle rotations in order to further expand the the properties angle rotations with complex numbers. Yeah, because in the last video, I think we talked about angle rotations and we discussed about the rotations from positive to negative. We have to, like in the number line, we have to multiply by rotate 180 degrees, but we also learned that we can rotate 90 degrees and 270 degrees, but it'll be imaginary numbers. But that's why they're useful, to expand, to give more knowledge on the angle rotations. Now, yeah, now one more thing. Complex numbers. Complex numbers are used for electrical engineering. Okay, and two is like thermodynamics. Thermodynamics. Okay, they're useful in uh, angle rotations. They help in angle rotations. Okay, and there's so much more. Like, no, they help. Like, mm, they help. They help to expand. Yep, to expand number systems. Okay, help to expand number systems. Okay, So these are like the main uses, okay, of the complex numbers. Okay. So like I'm gonna give you an example also, okay? Like for example, um, suppose you want to find, I'm gonna go here. For example, I'm gonna give a formula. Yes. So as you know, look, if the impedance denoted as Z is commonly known commonly known used in electrical engineering. And look, let me show the formula. The formula is is like Z. Look, oh my god, this is too big. Okay, yeah, this is big. Okay, so I just write the formula here. The formula is Z is equal to R plus, what was it again? Yeah, J K. And you might be thinking, what is the imaginary unit? This one. But you look, I'm gonna explain why it's not I. Here, look. The points are, look, R is the resistance, okay? Z is the impedance, and K, hold on, and K, uh, wait, sorry, wait, hold on. Actually, this was supposed to be X, okay, sorry. Yeah, I think it's commonly known for using X, so I'm gonna use this, J, X. And you might be thinking that the imaginary unit should be after this, but it doesn't matter. You know, you can write it either way. It can be KJ or JK, but you know. Okay. And yet, sorry, yeah. And X is the reactance. Let me tell you what it is. Okay. And guess what? J, look, J is used in place the main imaginary unit to avoid confusion. Used in electrical engineering. And yes, J, what are like J is equal to this. Okay, that holds also. So I just want to show the importance. Like don't think that these complex numbers, they're not important. Like you can put the values in, you just put the unit. But the main thing I wanted to make this video was to like to show the importance of why we're studying this. Okay, so like because we need to expand number systems, you know, like we have integers, rational numbers, but they're also complex numbers. Okay, because you know, like when we expand number systems, math becomes more interesting. Complex numbers, they show up in many G, like NEET exam, JAT exams, or like if you're in India, competitive exams. It's mainly used in physics, electrical engineering, thermodynamics. You know, hold on. I think thermodynamics. Yeah, thermodynamics and electromagnetism. No, it's used like everywhere. And yeah, guess what? Yeah, yeah. Complex numbers consist of real parts as well of a real part and an imaginary part. Yeah. So real numbers are also useful numbers. You understand? See, all of these number systems are important as well because without them, complex numbers wouldn't exist. Okay, so that's a step-by-step part. Okay, so yeah, just don't think that these are like. See, it's important to show why they're important. Like, yeah. And I think there's one more topic I want to show. Yeah, I'm gonna explain like. Okay, and yeah, I think that was all. Okay, yeah. Also, just one more thing. One more thing. After one more note, one more important note on complex numbers. Just an important note. Okay. Okay. So here's the note. Is that yeah. Usually, imaginary numbers are defined as the square root negative number. However, the thing is, we take any negative number to an even root. It is also imaginary complex as well. Okay? Yeah. So, okay. However, it is not used in many even roots other than two don't give a meaningful result. The result, the so the result is mainly complexity. Like what I'm saying is, you should know this, bro. Is that okay? Is that if we have okay, like if we have something like suppose we have something like if is an an even an even integer where n is a positive is an even is an even if n is a positive integer, then 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 guess what? Then okay, wait, hold on, integer, and x is a negative number. Then take a look. If we take this to the root 2n, this will be complex. Understand? Okay? Yeah. And yeah, of course, if it's even but if there's a negative sign, just put 1 as a numerator. Simple thing. But you know. And you also, one more thing, this is the same as x raised to the power of 1 upon 2n, a factor exponent. You can say either way, but just want to let you know. Because you should, and yeah, we've done topics like, so we've done the, what is the equality of complex numbers. I think explain it, but it's pretty simple. Like, what is equality means, like, equality. I'll just briefly explain it here. Like, if we have something like, I have to go somewhere here. Okay, so suppose we have something like a, if a plus bi equals another complex number c plus di, where c is a, b, c, d, where a, b, c, d are real numbers, then the following should hold. Look, a must be equal to c, okay, and bi must be equal to di, okay, or if you want to simplify it, you can say b equals d, because I just cancel it out. Okay, so you should mention this, that whenever you're verifying any equation like this, just make sure these two have to hold. Okay, so yeah, that's all. Yeah, and your properties are also easy, I think, but here I'll explain it. Like, if we have something like z1 into z2 plus z3, this is distributive. Wait, how long is the video? This is distributive, so this would be z1 into z2 plus z1 into z3. And yeah, this could be negative as well, but if it's negative, you can just write it as plus minus, like that. So they could be complex numbers, but it does not hold for subtraction. So z1 into z2 minus z3 is not equal to z1 into z2 minus z1 into z3. No, wait. Well, actually, this is equal. So this is equal. I was gonna talk about something else. Yeah, this same goes for subtraction here. So these two hold, okay. But you don't have to write the plus or minus. You can just write it. You can just simply write z1 into z2 plus or minus z3 gives z1 into z2 plus or minus z1 into z3. So this is known as distributivity. This is a distributive property over complex numbers, okay? Now, associative. If you're talking about associative, z1 plus z2 plus z3 equals z1 plus z2 plus z3. Yeah, you can verify this. If you get a question, you have to simplify the brackets. Yeah, I already taught you how to do the operations on complex numbers. It should be easy. However, z1 minus z2 minus z3 is not equal to z1 minus z2 minus z3. Keep that in mind, okay? Because this is subtraction. It's not associative, okay? Okay? So just make sure you will remember this, okay? And yeah, we have commutative as well. Commutative, it's that basically z1 plus or minus, no, only for addition. Yeah, z1 plus z2 equals z2 plus z1. It's a simple concept. Yeah, I'm explaining this because all these properties, they hold as real numbers, okay? And the thing, but there are some other number systems like quaternions, but those are advanced, and the properties are very different. Like, quaternions, they're not associative, but For complex numbers, since they're 2D, they have the same properties like real numbers. Even the real numbers are 1D, but still, is not equal to z2 minus z1. Okay, in this case z1, yeah, and this would not be true if z2 is not equal to z1, of course. That's already assumed, because if they are, then then why would you write 1 2? Okay. So now we're going to do the closure property. The closure property. Yeah. So yes, the sum of two complex numbers. This is in fact complex. The difference is also complex. Yeah, you can verify it. But however, it's not always the product. Not because the product and its conjugate is a real number. So like that's why this can't hold. And for division, division here. If we divide something like this, yeah, this could also be no. This is also not. Why? Because suppose we have something like a plus bi upon 1 upon a minus bi. This is also complex, right? This is a fraction. And if you simplify this, you get times a minus bi. So yeah, this doesn't hold as well. Okay, so yeah, those basically things. And yeah, one more thing. Yeah, I already explained that, complex numbers, real numbers, they can be expressed as complex number, with imaginary part being 0i, but it doesn't mean that they're complex. I explained that, So yeah. Okay, so I think that's all. If you have any doubt, let me know. If you think if I did something wrong, if any problem, just let me know. That'll be all. Thank you. Bye.